Welcome to Investigation 2.1, shirts and cups again. So essentially, or caps, I should say, not cups. Whoops, caps. All right. So in this investigation, you are looking essentially at that same T-shirt and baseball cap scenario where 8th graders were trying to raise money for a fundraiser. In this investigation, we're essentially looking at seeing how we can solve systems of equations. So if you remember, we can essentially create two different equations for this. We can look at how many caps and T-shirts were sold, like how many individual items, and then we could also look at the dollar profit that we create or that they made. And we can play around with that. And that's what you're going to be investigating in the investigation. However, in this, we're going to use one equation where we're going to look at a couple of graphs and look at a very specific situation, and then we're going to generalize it and look at some various equations. So we're going to be solving systems with that slope-intercept form, but we're going to be doing it with graphs and with what's called substitution. And it'll be very fun. So let's get started. First of all, we need to have a couple of words worth knowing added. Systems of equations is one word worth knowing, or words worth knowing. Systems of equations are two equations that we can compare. Usually with systems of equations, we are looking for one solution. And that one solution is if we were to graph these babies, if we were to graph one of them and graph the other one, we are looking for where those two lines cross and understanding what that point means. So typically we'll end up with an x-y coordinate pair, which then tells us that this is where these lines cross and this is the solution. These systems of equations are usually shown with this big bracket notation where you'll then have one equation and then you'll have a second equation. And they'll both be slightly different, or they could be exactly the same. And if they're the exact same thing, we have the same line, which is totally fine. The other word worth knowing is substitution. And this is where you are essentially solving for a variable and substituting or replacing that variable in another equation. And I will show you exactly what that means as we move on. So essentially you're taking one equation and another equation, and you are identifying a variable that is the same, potentially y, and you are saying, okay, well, everything in this purple equation is going to be equal to everything in the yellow equation. And you would essentially solve those two equations for x, and then you'd figure out your y variable that goes along with it. So substitution is another way to solve a system of equations. So far, what we've been using is graphing, and now we're going to use a new method, substitution, today. So here we go. Miss Lucero, she is a lady who had tiled around her pool. She had a square swimming pool, and the equations below, not elbow, sorry, below, show the estimated cost C in dollars for buying and selling and border tiles. So we had cover and surround it, C sub C is equal to 1,000 plus 25 times n minus 12. And then we had C sub T, which is 740 plus 32 times n minus 10. So tile and beyond versus cover and surround it. First of all, we need to write these two equations as a system of two linear equations. So they already are linear equations, so all we need to do to write them as a systems of equations is make this bracket and say C sub C is equal to 1,000 plus 25 times n minus 12. And the other equation, c sub t, is equal to 740 plus 32 times n minus 10. So we're just looking at those two equations and making a systems of equations out of it. Now our next step, I'm going to just move this down a little bit. We need to simplify each equation and graph them. So in order to simplify them, we're going to be getting rid of this parentheses on each one of the equations and turning it into y equals mx plus b form, because otherwise we can't graph it. So let's turn these equations into a system of equations, but have them be in slope-intercept form. So let's start off and do just that. We're going to do the distributive property for this first one, so we get 1,000 plus 25n minus 300, and then we're going to combine like terms, so then we'll get 25n plus 700 is our equation for c sub c. So I'm going to add that. C sub c is equal to 25 times n plus 700. Here's our next equation. We need to do the distributive property again. We'll get 740 plus 32n minus, move this over a little bit, 320. Now we need to simplify again. So we get 32n, there's my m and x, the slope in the y or the slope in the x, and then plus 420. So now we'll add c sub t is equal to 32n plus 420. So those are our two equations simplified. They've been simplified right there. We still have a systems of equations, and now we need to graph these babies. We need to figure out where everything hits. Now what's nice is we can see our n. This is essentially going to be our x value, and then we can also see that c sub t and c sub c are right there, and that's kind of in our y place, so we would be able to graph it based on our independent variable n, the number of tiles, and finding out the cost, which is dependent upon that. So I'm going to bring these two equations down, and we're going to start, and I'm going to graph these. So just a little bit of math magic, and we can look at and see what happens. Okay, so I've now graphed these two equations. You can see c sub c is in red, and then c sub t is in yellow. And as I graphed these equations, I did find a common point, which was at 40 tiles. We had $1,700. If we remember from this last book that we did with Say It with Symbols, that was the exact answer we were looking for. But what's interesting is as I was doing it, I was noticing that graphing this was really difficult. I could easily see how I could potentially, if I wasn't being incredibly accurate or if I was rushing things, that I could easily get something wrong. So while graphing is a good idea sometimes, I feel like it can sometimes be inefficient and inaccurate. It could be a waste of our time. So while I got the right answer, let's also take this concept and actually solve the systems of equations for cost in tiles and cost symbolically. So we have our system of equations where we have c sub c is equal to, goodness, I forgot already. C sub c is equal to 25n plus 700. There we go. 25n plus 700. And c sub t is equal to 32n plus 420. So what we're going to do in order to solve it symbolically, what helps is if we have the same variable on the end. We need to find the same cost, right? We're trying to find the same number of tiles that equals the same cost for both of the companies. So that means I can actually say that instead of writing 25n plus 700 equals c sub c, I'm just going to make this equal to 32n plus 420. What I did just now is I substituted, instead of writing c sub c on the end, I know that c sub t needs to equal c sub c. C sub t is equal to c sub c. They need to be equal if we have the same number of tiles. We're finding that cross section, or that one point where everything matches up. And in order to do that, we can essentially make those two equations equal. And from there, we're just going to solve it. We're going to do the math. So we're going to subtract 25n from both sides, subtract 25n, and we'll end up getting 700 is equal to 7n plus 420. Now we're going to subtract 420 from both sides, and we'll get 280 is equal to 7n, divide by 7, so we get n is equal to 40. Now in order to find the amount that 40 tiles gets us, we're just going to plug that back into one of these equations. We're going to substitute even further. So we get 32 times 40 plus 420, and if I did that math, I would get $1,700. Awesome, I found our corresponding point, and that's pretty sweet. So we're going to take this concept of figuring out something symbolically versus graphically with a very general set of equations. Practice with these random equations. We have x plus y is equal to 3 and x minus y is equal to negative 5. This is a question in your investigation for part C or D. I can't remember how far it goes. But what we're going to do is we are going to simplify both of these expressions and turn them into slope-intercept form. It's already a systems of equations, so let's do just that. Let's subtract x from both sides. So we'll end up getting, for our top equation, y is equal to negative x plus 3. And our bottom equation, we're going to subtract x from both sides. We would get negative y is equal to negative x minus 5. That means we need to get a positive y, so we're going to multiply everything by negative 1, and we'll get a positive y is equal to x plus a positive 5. So here is my systems of equations. We have y is equal to negative x plus 3 and y is equal to x plus 5. Those are my systems of equations. So we're going to find the solution graphically first, and then we'll do it symbolically. So then we'll do substitution. So let's first graph this. The very top equation, let's do in purple. We'll say it goes up 3, and then it looks like we have a slope of negative 1, so it goes down 1 to the right 1, down 1 to the right 1, down 1 to the right 1, and we're going to just make this graph like that. Oops, almost. Cool. And then this other one we're going to do in yellow. So we start at 5 for this one, and this one goes up 1 over 1. It's got a positive 1 slope. So we're going to make this graph, and it looks like I just found my intersection as I moved backwards. So my intersection looks like it happens right here at negative 1, 4. And if you notice, that was actually kind of hard for me to, even though I knew I hit that point, it was kind of hard for me to find it because it was in a graph. It could be easily inaccurate, and especially if I'm doing it with an iPad. All right, and a graph like that. So let's check and see if that graphical equation and answer is the same as if I were to solve it with substitution. With substitution on this baby, we have these two equations, y is equal to negative x plus 3 and y is equal to x plus 5. We have y's in both of our equations. So essentially we can say y is equal to y. We can say that our purple y is equal to our yellow y. And if that's the case, that means we can make our equations equal to each other. We have negative x plus 3 is equal to our purple y, and our other equation is x plus 5. That's our yellow y. From there we can just solve for x. So let's do just that. I'm going to add x to both sides so I can get or add an x to both sides so I can get my x's on one side of the equation. So I have 3 is equal to 2x plus 5. From there, I'm going to subtract 5 from both sides. So I get negative 2 is equal to 2x. And now let's divide by 2. Divide by 2. Negative 2 divided by 2 is negative 1 is equal to x. That's exactly what we got for our x answer. Now we're going to put this information into one of these two equations. Doesn't matter which. We're just going to do it. So we get, instead of x, we're writing a negative 1 plus 5 gets me 4, my y value. So we were correct with our graph. And symbolically, this makes just as much sense. I want you to play around with this concept of solving equations with substitution or graphing. And as always, if you have any questions, make sure you ask. We're going to be moving on to 2.2 tomorrow, and yeah, it'll be fabulous. Or Monday, I should say, and it'll be fabulous. Thanks so much for watching, and I'll talk to you later.